Over the last few sessions, we've been talking about light and temperature in lakes and other ecosystems, and I'd like to combine those together today to talk a little bit about zonation of aquatic systems, give you some ideas about what kinds of zones there are, but also talk about how those different zones combine together to create successional stages in lakes as lakes succeed or change from one state to another. The objectives that I have for today's presentation are, first, that you'll learn about ecosystem succession, mostly with respect to ponds and lakes. Then I'd like you to learn the rudiments of aquatic ecosystem structure and zonation, and I'd like you along the way to understand why zonation is particularly important to the function of aquatic ecosystems, and then also learn how characteristics of those ecosystems alter zonation in general, stopping by talking about marine systems as well, which is one of the more complex aspects of ecosystem zonation in aquatic systems. First, I'd like to review again what we know about trophic status. We have oligotrophic lakes and eutrophic lakes, and oligotrophic lakes are distinguished from eutrophic lakes in that oligotrophic lakes have very little in the way of nutrient material in them. And because of this, they have very low primary production, so low plankton abundance, a very high richness of plankton, but nothing like algal blooms. So they tend to be very healthy systems with very low rates of productivity, very diverse flora and fauna. But when we add lots of nutrients to aquatic systems and make them into eutrophic ecosystems, they tend to be shallow, and that's no accident, because they create a lot of organic matter through their very high aquatic plant production, plankton production, and sedimentation rates. And so they tend to sediment in or fill up with sediments as time goes on. For the time being, we can sort of leave behind dystrophic systems. Those are mostly bog-like ecosystems that are fairly constant and stable over time, although over the very long stretch of time they will tend to fill in and succeed in various ways as oligotrophic ecosystems change from oligotrophic lakes to eutrophic ones. Eutrophic lakes change and succeed toward wetlands. Bogs also eventually will become wetlands, and eventually meadows, but on a much slower time scale. This diagram shows essentially what happens over the lifetime of an aquatic system, a pond or a lake, that they're not just static, that they change over time, and they change rather radically over time. They usually will start out fairly oligotrophic and free of nutrients with very little primary production, nicely well-balanced systems. But as they grow, a lot of aquatic plants, especially those in the shallow littoral zones, as we'll learn a little bit later in this talk, as that littoral vegetation grows, it creates a substantial amount of accumulating sediments. These sediments are preserved over very long periods of time. In fact, millennia. Lakes are very famous for preserving things in their sediments, and eventually those sediments build up and are preserved so well that we close in all of the open water and essentially create a meadow-like environment. So that's the basic aspect of lake succession. There are many aspects of production and filling that lead to succession of a lake toward a wetland, and those are shown in the list on the left-hand side of this page. And clearly things can blow into them, and we find a lot of blown-in material that we call autochthonous material, allochthonous material, because it comes in from the outside. Pardon me. And there also are sediments brought in by inflow and runoff, and these are also allochthonous materials coming from the outside. Wave action will erode the shores and focus sediments, and plants growing in this system, as you see there on the left-hand side, produce organic matter also that enhances sediment deposition in these systems. It's not just plants that will build up, however. We find well-preserved animal remains down in the sediments, shells and other materials, and sometimes filling is hastened by draining or changes in the drainage of a watershed, or when inflows are cut or outlet channels are enlarged. many aspects will accelerate or decelerate the succession of an aquatic system from a lake or pond-like environment to a wetland and eventually a meadow environment. Here's a series of photographs that I took on the border between North Dakota and Manitoba. This is a fairly recently glaciated area, a little bit younger than Iowa, where I currently live. But you'll see here a very early successional stage, a fairly deep lake with very little fringing vegetation around it, although it probably is building up sediment down in the bottom of this that basin. As time goes on, we begin to develop a fringe of littoral vegetation around the outside of the lakes, and that encroaching vegetation moves inward and eventually builds up substantial amount of sediment in a sort of a bench-like or area around the edge, and also focuses some of those sediments down into the deeper waters of this pond. So you can see some increasing productivity. The edges are beginning to, the emergent vegetation at the edges is beginning to grow outward into the water, and sediment is clearly building up. If we look at a slightly later stage of succession, this is the extension of the littoral fringe. So this littoral fringe area is getting farther and farther out into the water. Over in this area you can see some submergent macrophytes, some aquatic plants that are underwater, aquatic plants underwater here, floating leafed plants, and emergent vegetation around the edge. Again, moving ahead in succession, what we're seeing is a very dense littoral growth of emergent vegetation. These are aquatic plants, but have their most of their vegetation out in the air. They're called emergents. You also see a lot of submerged vegetation growing in a very patchy configuration within the lake underwater. This littoral fringe is closing in. It's closing in fairly rapidly, and of course, as you get more plant growth, you have more sediment build up, the lake gets shallower faster, and the outside begins to close in. Again, well, sometimes this whole process is helped along by cutting it in half with a highway or increasing sediment flux or flow into the system. But here you can see that littoral vegetation has moved way out into the open water, is beginning to close it in, both in the upper of these two and the lower. Very little open water, lots of emergent vegetation around the outside, and we're beginning to see the traces of what the lake used to be. Now, pretty soon in this process, because of the acceleration of organic matter deposition, you'll see almost meadow-like vegetation all the way around the edge, maybe only a little tiny patch of open water in the middle of this, in the middle of what used to be a lake. And eventually, as that vegetation closes in, you have a meadow. You have almost no vegetation, aquatic vegetation. You can see the outline of what used to be the bottom of that lake in the past, and you can see that this used to be deeper. It's slightly more hydric or water-loving plants living out in the middle, a little bit more terrestrial plants at the outside. But that's basically the process of lake succession. It's the littoral zone itself that closes in and begins to close it and turns it essentially into a terrestrial environment. So this kind of begs the question of what the zonation is, because all along I've been talking about littoral zone plants, and the littoral zone is this area near the edge, and we're going to spend some time looking at the structure of aquatic systems and what these zones are and what we call them and what are their characteristics. Now, you may think this is an unimportant thing to do, but it is really important, and the reasons for this are several. First, different zones of aquatic ecosystems contain completely different types of organisms. If you're interested in fishing, probably most of the fish you catch are littoral zone dwelling fish. If you're interested in whitefish or tullibees or smelt or some of those other pelagic fish, then I make a mistake, but many of the sport fishes live almost entirely in or around the littoral zone. Different zones of ecosystems function really differently. The pelagic zone, the open water of lakes, tends to have plants that turn over very rapidly. The shallow waters have plants that stay there quite a long time and build up a great deal of diverse structure in that littoral habitat. Some zones are much more important than others when you're considering the management or conservation objectives. And again, the littoral zones tends to be extremely important from the standpoint of wildlife and fisheries. The open water and the clarity and beauty of it is also very important to other kinds of recreational activities, and so we end up managing ecosystems to enhance both of these kinds of areas. And also, finally, sampling and experimental techniques vary among zones. The open water, we can simply throw essentially a bucket in there and take a sample that's representative of the environment, whereas sampling a littoral area with diverse kinds of vegetation, such as those you saw in some of those previous slides, is really a complicated affair. So lots of reasons to pay attention to aquatic ecosystem zonation. The zonation of streams is essentially, is simpler in a way. Basically, streams are divided into pool and riffle habitats. Pools are the deep places, and the shallow places are called riffles. The riffles tend to be very productive. Lots of organisms sit in the pools and wait to be fed by riffle animals and plants coming out of the riffle areas. The riffles and pools are usually formed by the meandering of a stream, something that we'll talk about quite a bit in subsequent discussions. So pool and riffle habitat, and we also talk about runs and other kinds of habitats within streams. Today we'll concentrate more on the lentic waters, however, and spend much more time discussing the zonation of ponds and lakes. Here's an illustration from the CALF book that I'm sure you've run across, or something very close to it. And this shows some of the basic aspects of the biological functioning of aquatic systems. There are exchanges with terrestrial environments, to be sure, but there are lots of exchanges within the aquatic systems, but also within areas of aquatic systems. Over here in the shallow water, you find macrophytic vegetation. Out here in the open water, you find planktonic vegetation and bacteria, and all sorts of dissolved nutrients and dissolved organic material, as well as down on the bottom where sediments tend to be deposited, you find a lively benthic fauna as well in this sort of sedimentary environment. So lots of different living things, but they live in different places in these aquatic systems. Here's another rudimentary look at zonation, and I think you can see clearly this big yellow area out here is the pelagic zone. Pelagic refers to that part of a water body where organisms are freely floating, and those things that are freely floating will be things like phytoplankton. The littoral zone that I've been talking about in this whole discussion of lake succession is the place where illumination penetrates to the bottom, and therefore rooted plants can grow and thrive and create diverse habitat and very high rates of primary production. Light penetrates to the bottom because lakes are divided into photic and aphotic zones. Simply means areas where there is light, areas where there is not so much light. Dividing them is the compensation depth, which is normally about 95% of surface illumination. But this is the place at which aquatic plants can just make a profit. Below this level, there's not enough primary production to allow them to continue to thrive, where above it, the phytoplankton can grow actively. Now you'll notice here that the photic zone and aphotic zone don't always correspond with the epilimnion and the hypolimnion and the metalimnion. Quite frequently, the profundal zone can actually be deeper than the hypolimnion, or can can consist of more than the hypolimnion, in fact the metalimnion and part of the epilimnion, depending on light penetration. Sometimes light penetrates below the metalimnion. In that case, we'll have primary production occurring in the hypolimnion. So there really is some correspondence between the thermal zones of lakes and the photic zones of lakes, their interplay leads to some very interesting ecological aspects of these ecosystems, but they do not always correspond well with one another. Photic zone is not equal to the epilimnion. The aphotic zone is not equal to the hypolimnion. They are determined one based on light and one based on temperature, or in the case of a meromictic lake, the stratification will be determined based on salinity in some cases. The littoral zone structure is pretty simple. The littoral zone itself is divided into several zones, as well as zones that are in fact outside the area where there is normally water. Now the eulittoral zone, that is to say the true littoral zone, is defined by the high-low water area, and it's the area that's disturbed by waves. So the eulittoral is the high-low water, where water will come up this high and down this low. That would be the eulittoral, and it is often disturbed by wave action. Above the eulittoral is the supralittoral zone, and this is an area that receives quite a lot of spray from waves, and it is usually very wet, and you will often see growth of very water-loving plants in that area, and basically riparian zone plants that can tolerate a substantial amount of water, spray, as well as having their roots immersed in water as they will be below the water table. The epilittoral is the area where there's no spray, but is still in the riparian zone of aquatic systems. Now, below the eulittoral, we find three different gradations of the littoral zone. There'd be the upper, middle, and lower littoral zones, and they're basically defined based on the different kinds of plants that grow there. The upper littoral tends to have emergent vegetation, the middle littoral has floating leaved vegetation, and the lower littoral tends to have submergent vegetation. Now, below the lower littoral, we find the littori profundal, or sometimes we call this the sublittoral zone. And this area will have some rooted aquatic plants on occasion, often things like mosses and other kinds of plants that can grow under very low light and at very deep depths. And often it will be just clumps of algae that will be found in the littori profundal zone. The profundal is the deep. You've heard the word profound. Probably it means the same thing. Very deep. If you're having profound thoughts, they're deep thoughts. The profundal zone is the area that is unvegetated and in which much of the profundal benthic organisms live. Now, if there's a lot of wave action, then the littoral zone is changed just a little bit in that you have a surf zone within the eulittoral zone. The upper littoral zone is often very compressed because the emergent vegetation has a hard time growing there. The middle and lower littoral will be quite similar to the middle and lower littoral, where there are not a lot of waves, and of course the littori profundal is very similar to that is found in a lake without much wave action. Waves break in the surf zone when the depth is 1.3 times the wave height or less, and what that means is usually this is in a couple of feet, let's say, 2 to 4 feet of water would be where waves are breaking in the surf zone in most lakes except for the very largest ones. The structure of marine systems is quite different again, in that first thing you should realize is this depth scale here. We're going down to 6 kilometers in depth. What is called the sublittoral zone, or the sublittoral or the littori profundal zone, in marine systems goes down to about 200 meters, basically because of phenomenal amount of light that it can penetrate through the very clear water. Below the sublittoral zone then is the oceanic province and the bathypelagic. Bathy means deep pelagic, bathypelagic. Meso is middle pelagic, and obviously surface water in the first 200 meters is called the epipelagic zone. Now down here at the very bottom of this diagram is something called the hadal zone, which is called the hadal zone quite reasonably, since it is deep as Hades, or deep as hell, basically. Very, very deep, very, very deep water in some of the oceanic trenches, and this has a very special fauna that's found within it. Okay, at very, very great depths, down to several kilometers in depth. Now the littoral zone, littoral zonation in the sea is different again from that in lakes and ponds, and this is a diagram taken from Stevenson and Stevenson's very early work in the 1970s on the intertidal zone. And now the word intertidal means simply between the tides, and the tides that this life occurs between is extreme high water of spring tides and extreme low water of spring tides. Spring tides are the largest tides of the year. So basically the supralittoral will be above this intertidal zone, and then because of the action moving back and forth of the of tidal flux, we will have a supralittoral fringe at the upper layers around extreme high water, a sort of a mid-littoral and an infralittoral fringe, and then an infralittoral zone below it, all defined based on their tidal frequency. Another factor influences the thickness and function of the littoral zone in marine systems, and you should be able to get this intuitively if you think about this spray zone in the littoral of lakes. In oceans and seas, the spray zone can be quite large if the shore is not protected from wave action. If it is protected, then it will be somewhat narrower. So we have two factors in play. We have the range of tide, so these are seas with large tidal ranges on the left and tideless seas on the right, very much like the Mediterranean, for example, which has extremely little tidal flux or tidal variation. But in every case, exposed zones or exposed coasts have much broader littoral zones than do those coasts that are protected, basically because the spray zone and the effect of waves, wind and wave action, can move water to a greater degree and add to the tidal variation that one sees in any particular system. This can be looked at as a simple graph. Here we have an exposed shore, a sheltered shore, but we've collapsed the tidal variation here, so we don't have to think about that. Here's extreme high water of spring tides and mean high water of neap tides. So a variation in tidal variation here. But of course in the exposed zones there is a very high reach of spray, and so some of the marine organisms can live to a much higher level on those very, very exposed shores. So in summary then, for session 6, aquatic ecosystems are structured by light and substratum, and the large and small scale factors influence aquatic ecosystem function within those ranges. Aquatic ecosystems are divided into littoral and pelagic zones, and then those littoral and pelagic zones are further subdivided into different areas depending on things like the amount of wind and wave exposure, the amount of tidal variation in marine systems, and a variety of other factors. Littoral zone is finally subdivided into many zones that influence community composition, and also marine and freshwater ecosystems are very similar in their zonation, but differ in zonation due to principally to the influence of tides.